Now, for those of us in the room who are finite element nuts, we have an exciting result. There's actual error bounds. We'll always complain they don't have, and Mark's going to tell us about.
So, I should begin by thanking David, Hillary, Matt and Colin for the invitation to be here. It's nice to be back at the Newton Institute, because the last time I was here was 2001 when I was actually an organizer, so they don't realize how much work they're actually going to do, but I was an organizer for a 6-month program, and the title of that program was Computational Challenges in PDEs. So it's very much aligned with this, but I'm quite excited to come to this, because you know what it's like. You go to conferences and you see the same faces over and over again, and I hesitate to say the same talks over and over again, but perhaps you get the idea. So it's interesting to come to a conference where I basically know nobody, particularly if I'm going to be here for 4 months. So one of my objectives being here is to try and do something new, do something different, and I'm very interested to find out the kind of models you're looking at and to try and bring some mathematics to it. So I'm a mathematician. I'm going to make no apologies for that. I'm going to prove some theorems today. I'm going to make no apologies for that, but I'm very interested in developing collaborations. It's really a good place to be for 6 months, and this program of research I'm going to describe today was essentially instigated as part of that program. It's very interesting at Newton Institute because it has all kinds of kind of quirky traditions, and I overheard a conversation at coffee yesterday where people were saying, so when you had to fill out the accommodation form, it asks who you would be prepared to share with. So I didn't know anyone here, so I said, I'm willing to share accommodation with anyone. And then I found out I had accommodation all to myself, so I was very pleased about this. Well, I was pleased at first, then I started to feel a little bit upset because I realized that everyone else has said they're not willing to share accommodation with Ainsworth. So anyway. So what can I bring to this party is the question that I ask myself. So I work on all kinds of things: high order methods, low order methods, HP methods, spectral methods, wave propagation, fluids, elasticity, but not the kind of models that you're looking at. So that's one thing I'd be interested in. But what can I bring to this party? And what I'm going to describe now is this program of research that was really initiated at the Newton Institute before. And, well, really the issue is, let's go back to a classic result. The basic issue is how much can you trust your numerical computations? And I think this is fundamental for everyone. So in principle, everyone is interested in how accurate are their numerical computations. I heard some discussions yesterday where it wasn't clear to me what you meant by the distinction between the error in your model and the error in your discretization. In the community I work in, the adaptive finite element community, there's a very clear distinction. You have an idealized model that you're trying to approximate. You may have a dimensionally reduced model or some model which approximates that. That's modeling error for me. And then you have discretization error, which comes when you apply a specific numerical method to approximate the continuous model. So modeling error is the error in approximating maybe a higher dimensional or more complicated physical model, which you believe to be the truth, by a simpler one. And then there's an additional source of error when you come to discretize. I'm only going to talk about discretization error today. So let's go back to this classic result from Babushka and Reinbold. It's for the Poisson equation. Let me get it clear. I don't care about the Poisson equation. I don't want you to go away with the message, Ainsworth is interested in solving the Poisson equation faster and faster or more accurate. I don't care about the Poisson equation. I am going to talk about the Poisson equation because what I want to try and do is to show you a framework, and there's no point in me putting it in the context of 3D elasticity or some other thing, because you'll be the details will be obscured. I want to try and show you the basic ideas, what can be done. The reason that I'm going to do that is because essentially everything I'm going to say, because we started off with Poisson type problems, we then pushed this forward to elasticity problems in 2D, elasticity in 3D. We have guaranteed computable bounds for finite element approximation of 3D elasticity. Nobody else has that. Guaranteed computable bound means you do your finite element of computation using whatever scheme you like. So what I'm going to say applies to discontinuous Galerkin, non-conforming finite elements, conforming finite elements, mixed finite elements, stabilized finite elements, Everything, we've basically tried to develop this to the point where it's of use to practitioners. The bounds we've used for 3D elasticity are now being used in a code that's used to certify pipelines in the North Sea. So, while I'm going to talk about the Poisson equation, I don't care about it. I do care about the structure, and I'm interested in developing usable bounds that end users will use. So this is really, if you come with a new application or a new method, I'm interested to see whether I can do something for that. But let me take you back to essentially the start of our program at the start of the millennia. And there's this classic result from Babushka and Reinbold. So you've got a simple problem, and then what we have is, for example, a finite element approximation to this. We have an error. And then if you define this quantity here, so it's the element size squared times essentially the residual in this, so you look at f plus how well your Laplacian of your approximation approximates f. That should be 0 if you have the exact thing, so there's a residual there. And then there's something that measures the jumps in the normal derivatives from element to element, because your finite element approximation is continuous in this case, but it does have jumps in the normal derivative. So that is a quantity which can be computed. All of these are just available to you from the finite element approximation in the data. And the classic result, which really wasn't settled until the late 90s, is this. And what it says is that this quantity you're computing provides a two-sided bound on the gradient of the error. So what it says is if your estimator goes down at a certain rate, then your error will go down at the same rate. But at that time, these constants were magic constants. Nobody could tell you what they were. There exists positive constants independent of the mesh size and the solution such that this holds. And that's good, but for what I mean, that's a nice result. It's a classic paper. I'm not criticizing what Babushka and Reinbold did. I think that's really a very big step forward from what was done before, but it's not the end of the story. And if we criticize this a little bit, you can ask various questions. Let's suppose, as is the case with people I collaborate on the North Sea oil stuff, that they don't refine any meshes. They have one mesh. It costs a fortune to generate the mesh. They have one mesh. They approximate on that mesh. The question now is that they may have to stand up in court and justify saying that this pipe was safe or not safe and so on. So they don't have any option to do mesh convergence studies, anything like that. They've got one approximation. Question is, how accurate is it, and are you willing to sign away your company or your life that this is correct? So from that point of view, this result is useless, because it says that the gradient of the error is less than some constant times this. Unless I know what that constant is, that result is useless. So that's one kind of reason why you might like to have the constant. Well, why else might you want to have the constant? If you're doing adaptive refinements, you don't want to refine down to machine precision. At some point, you're going to have to call it a draw and stop. What's the point in solving to fractions of a % accuracy if you don't really have your accurate data? So if you can balance the error in your iterative solver against the error in the discretization, the error in the data, the uncertainty in the geometry, and so on, then that's obviously the best thing to do. But unless you have knowledge of these constants, you can't do that. I remember one time when I was with Ivo Babushka, and we were talking about this issue of constants, and one of his mathematical colleagues came in and says, why are you worrying so much about constants? I don't care about the constants. I only care about rates of convergence and so on. So Babushka, who's got a very quick and acid wit, immediately responded, you don't care about the constants? Really? Then why are you worrying what your salary is this year? So we all care about constants to one level or another. So at that point, this is the kind of kicking off point. Can we, first of all, get computable bounds? We can calculate this, but we don't know what the C is. So I want to try and develop bounds where all the constants are specified. What you compute really is a bound for the error. Takes account of oscillation of data, the fact the data may not be smooth, takes account of all the effects that you're interested in. So there we are. So let me just jump forward a little bit. Right, so now the question is, how am I going to try and present this framework? We've applied this framework to, as I said, elasticity, Stokes flow, convection diffusion, all kinds of problems, all kinds of discretization schemes to some extent. I could pick any one of these to talk about. The one I'm going to choose is discontinuous Galerkin, because that's the one I've seen on the board most in the first 2 days. So this is I'm going to try and explain this general framework by showing you how it works in a specific case. So I'm going to talk about discontinuous Galerkin. This is some work with a grad student of mine who's now at Rice University, and this is really the results of 3 papers. So we go back to our Poisson equation. I don't care about Poisson equation. We've got a source term, boundary flux, permeability matrix. This can be jumping around, actually. We care about, for example, very high variations in permeability. Does the performance of the estimator degenerate, and so on? I won't emphasize that today, but we are interested in the dependence or the sensitivity of our bounds on material properties like Peclet numbers, so on. But I won't emphasize that too much today. So what kind of scheme am I going to talk about? It's going to be an adaptive refinement scheme. We have an initial mesh, which is just some regular quasi-uniform mesh, sharing common edges and so on. We refine that mesh by subdividing a marked set of elements into 4 congruent triangles that generates hanging nodes. That's the kind of refinements that we're talking about. You can have any number of levels of hanging nodes. So there we've got 3. You can have as many as you like. Our analysis takes account of that. There's more. Of course, the bounds degenerate with the more levels of hanging nodes, but we can say how they degenerate. Okay, so that's the kind of meshes. Take a particular mesh. My finite element space is going to be functions that are in H1 on the partition, so they can be completely discontinuous from one element to another. For simplicity, I'm going to talk about the case when they're affine on each element. We've got results which allow you to have any order on any element, different orders on different elements. I won't bother you with the details of that. We then have a bilinear form. So this is the usual mess that goes up on DG slides. We've got this part here, which is basically the piecewise gradient. We have an interior penalty term, which penalizes jumps across elements of some magic parameter kappa. Again, another constant, which is sufficiently large, will make the method stable. And then we've got the usual stabilizing flux terms with some thing here. I don't care what flavor of DG you like. You can choose tau to be whatever you like. You get all the different flavors there. So I'm going to go through this very quickly because essentially if you know this already, it's boring for me to do it. And if you don't know it already, you're not going to kind of get it. This is the DG thing as usual. There's the right-hand side with the usual stuff. So if you go with tau equal to 1, it's SIPG. Tau equal to -1, it's BOB or non-symmetric IPDG. With tau it's incomplete. Everyone can have their own choice. I don't mind which one you choose. Everything I say will work for all. This is well posed provided kappa is sufficiently large. Again, a constant. What does sufficiently large mean? I sit in the audience listening to these talks. So what's sufficiently large? Oh, we always choose 10. Okay, why is 10 work? We'll have to think about that. Actually, we figured out how you should choose kappa so it works. I don't like these constants. Here's a theorem. Let rho k be the spectral radius of the element stiffness matrix. If kappa is bigger than this, something to do with the spectral radius of the stiffness matrix, something to do with the nature of the method, that is sufficiently large. Okay, so I can kind of, well, let me just, this is a fully explicit bound on how large your interior penalty parameter is, independent of numbers of levels of hanging nodes. I've read papers where they say it depends on the number of levels of hanging nodes. It doesn't. Proves on all the existing things. All right, so let me go quickly through this. I won't dwell upon this. Is just something to bug people. Let's get to the meat. So a posteriori error bounds. A posteriori means I do a computation. I now have an additional piece of data, which is the current finite element approximation. How can I make use of that to assess the error? So here's my objective. I would like to derive a computable upper bound for the error in the energy norm, and or the DG norm. Some people want to estimate the error in the DG norm. For me, this is basically a parameter-dependent norm. What's the meaning of estimating the error in a parameter-dependent norm? If you want to do it, you can do it. I'm more interested in estimating the error in this broken energy type norm, but we can also give you the same results for this as well. Because it's such a simple problem, such a simple scheme, we're going to have to test ourselves a little bit here. All constants should be given in the upper bound. The thing you compute is a number. That number should always be an upper bound for what's coming out for the error in your approximation. None of this if the mesh is sufficiently fine, if the elements are sufficiently regular, if the data, none of that. What you get from the computer is a number. That number should be bigger than the error in your approximation. That's what I mean by that. There shouldn't be a constant in there if I choose it sufficiently large and so on. All constants should be specified and it should be an upper bound. It should be a good upper bound. Of course, I can find lousy upper bounds that don't even go to 0. It should be a good upper bound. It should go to 0 at the same rate as the true error. It should give you an indication of what the local error is. This should be possible to use this as an adaptive refinement indicator. There are theorems now which have been proved. One of the things we identified, one of the challenges, was to try and quantify what you attain by adaptive refinement. There are now theorems that say if you do an adaptive refinement algorithm with this step, then what you get is an optimal sequence of approximations. So the theory of adaptive finite element methods and convergence is really quite well developed now. There's been some very sophisticated approximation theory results. It brought in new talent from approximation theory, talent from computer science, and there's really been a big effort, and now there are theorems that say if you do this adaptive algorithm, what you get within a constant is at least as good as what anyone else will design. That's quite a high-powered result. The key to that is that you should have an upper bound for the error. What really drives it all is an a posteriori bound. The a posteriori bound should be a global upper bound and a local lower bound. So I'm going to ask that this does the same thing. This shouldn't just work if the true solution is smooth. It should work even if the true solution is not smooth. And also, well, you see I'm at Brown now, but I used to be in Scotland. The Scots have a reputation for not wanting to pay very much money. Where I come from is Yorkshire, and they have the same reputation. So I used to say I'm the meanest person in the UK. I'm still mean, but I'm not in the UK, so I don't want to pay much for it. If this is going to cost me 3 times the cost of a solve, too much. This should cost practically nothing. So keep your eye on that, because I don't want you going away saying, well, you have to pay so much to do it. It's very complicated. If you see any point where I'm doing too much work, stop me, because believe me, I don't like doing work. So what I get out of this should be very, very cheap, almost negligible, but not cheap and nasty. All right, so here's a result which is kind of key. This is the error in the flux. So I'm with Poisson problem or elasticity problems, I'm typically interested in the error in the stresses and strains and so on. So the error in the gradient approximation. So A times gradient of B. This is a distributional derivative, so there's some funny business going on there that you needn't concern yourself with. But we can split this into a vector field here plus the curl of something. Now this thing here, this chi, belongs to the original finite element space, the space of admissible displacements. And it satisfies this. It's simply the projection of this finite element flux error onto the conforming space. So this is taking out as much of the conforming error as possible. So I call that the conforming error. What's left measures the jumps in the finite element approximation. It's not apparent from this, but it does, and that can be shown later. So then you have a non-conforming error that belongs to some funny space that I'm not going to bother you with. It doesn't actually play any role later, but is needed for the theory, and it satisfies this problem here. So again, it's kind of projecting this gradient onto curls now. The significance of this Helmholtz type decomposition is orthogonal in the broken energy note. What it means is that we've now taken this error, we've broken it into a conforming part, a non-conforming part. I'm going to estimate the conforming part, I'm going to estimate the non-conforming part. If I can get computable bounds on both, add them together, computable bound on the sum. It's an orthogonal decomposition, I lose nothing by this splitting. How to estimate the conforming error? Now, I emphasize that what we did works for almost any kind of finite element scheme. The devil is in the detail, because if you're going to get a good computable bound, it's not going to be the same scheme for the same program that works for every scheme. My policy is I want to look into the details of the method, all the hidden properties of the method, and I want to extract out the properties of that method that can be used to get a good computable bound. So that's where the devil or the art comes into it. For different methods, it's harder to kind of see what is the key thing that you can exploit to get a very good computable error bound. Now, the big thing about DG, or one of the big things about DG, is that it's locally conservative. This is this is enough justification to use DG for some people. So this is a big deal. I want to use that property in a significant way. That's the key thing. It's locally conservative. I'm going to make use of that. So if I define fluxes in this way, so these are kind of piecewise smooth, so they basically depend on the jumps in the average flux weighted with the jumps in the approximation. If I define these things, these are locally conservative. The DG method is locally conservative. Keep that in your mind. I want to exploit that property. Okay, so how to estimate the conforming error? It's really very easy. Take your favorite test function. Then A times the gradient of the conforming error is this. That's just the definition. I now write the gradient of the error to be the gradient of the true solution minus the gradient of the approximation. So the gradient of the approximation is there, and the gradient of U, well, U satisfies the original problem, so that's just the data in my problem. Everything is now computable there. There's nothing that's unknown there, but of course that's still an infinite dimensional problem. That's going to be too expensive. What I'm going to do is I'm going to replace that one big problem by lots of small element-wise problems. You can't do this for the original approximation because you need global transport of information. But now I've resolved the global transport of information. I've got the finite element approximation. That should have basically figured out the displacements and the rotations and so on, or the averages. So I shouldn't have to go back to a global computation. I should be able to proceed element-wise. So that's what I'm going to try and do here. I'm going to localize this thing, so rather than one big thing from the whole domain, into a sum of contributions from the elements. So that breaks into the sources over each element. That breaks into the sources or to these DG fluxes. And that one just breaks into contributions from the elements. Okay, now here's a supposition. We'll worry about this later. Let's suppose I can find a vector field sigma such that it satisfies this. Why would I want to do that? Well, the thing here, this is what I want to try and get my hands on. Now that's in a little bit of a messy form. There are ways to proceed from that, and actually you'll get the Babushka-Reinbold estimator if you proceed in one of the various ways from that. I don't want to do that. I want to depart from what they did. What I do is I introduce a vector field that satisfies this. It's not obvious one exists. If it exists, it's not obvious how to find it. We will worry about that in a moment. In that case, that gives me that the gradient of the conforming error can be split into these element contributions, and now the result's staring us in the face. We do a Cauchy-Schwarz simplify, and what we get is that as a guaranteed bound, if sigma's in hand, this is computable. That is a guaranteed bound. There's no constant there. The constant's 1. It's known. You compute that. That is a guaranteed bound on the conforming error. Hooray. But what about sigma? Well, here's a key observation. I don't care what sigma is. All I care about is what this norm of sigma is, this weighted norm. Doesn't matter what sigma is, but it does depend on that. So if I can save more time and effort, remember I'm the meanest man in the UK, I'm going to do it. If I can compute that without getting sigma, then I will do it. How to construct sigma? Well, first of all, is it obvious sigma even exists? Because if I choose v to be a constant, this side vanishes. Does that side vanish? Well, that vanishes, and then that vanishes because dg is locally conservative. That's how I'm exploiting the key property of dg. So sigma exists. It's not unique. Well, I only want one sigma that works. So there we are. If I assume that f and g are piecewise polynomial just to avoid technical difficulties, that assumption will be removed later. It's not necessary. It's just to avoid distracting details. Then you can compute a sigma. Now, let me tell you how you compute the norm of sigma. So here's an element embedded in the middle of a DG mesh. I would like to compute the norm of sigma over there. So there are all these nasty real elements around it. This one has got no hanging nodes. The neighbors do. So the DG flux is a discontinuous piecewise polynomial on the boundary. So what I'm going to have to do is, if you think about what this means, I need the normal component of sigma to equal the normal component of g minus the normal component of the gradient of the true solution. So this already starts to look a little bit messy. Sigma's got to be messy because it has to be a different piecewise polynomial on each of these segments. And if I've got arbitrary levels of hanging nodes, that starts to look messy. So I'm in danger of spending too much time and effort on the estimator here. But let's not be deterred. Let's go back to a simple situation, no hanging nodes. What I then have is I have basically a difference between the flux and the approximated flux on here. That's a piecewise polynomial, so is that, so is that. I'm assuming the data's piecewise polynomial for the moment, so this means I've just got 3 pieces of data. One piecewise polynomial, one there, and one piece of data in there. I can then find an approximation from Rabiat-Thomas space. I won't bore you with the details of that, but there exists a vector field in the Rabiat-Thomas space that satisfies that property. That's easy to be done. You don't need to know how it's done. What you need to know is how to compute this. How you compute that is you take these 3 pieces of data, these are piecewise constants, form a vector from them, compute a little 3 by 3 mass-like matrix which is weighted with the geometry of information, the material property information, compute a little 3 by 3 matrix, work out that vector product there, and that gives you a number. That number is equal to the value of sigma. You don't need to know what sigma is. You can now implement this in your code. You calculate that, work out that. That is your value of the norm of sigma. That is a guaranteed upper bound for the conforming error. What if we've got hanging nodes? Now it starts to look complicated because we've got different polynomials there and there. This could start getting expensive. What we do is we introduce a virtual refinement. Some people have advocated meshing this domain in here and then proceeding from that. For me, that's too expensive. If I had to talk to, for example, my collaborators from industry and I said, by the way, to get the error bound, you've got to do another mesh generation, they'd just laugh at me. But some people advocate that. I don't advocate that. I introduce a virtual mesh refinement there. It's never going to exist. I'm going to now define residuals of normal fluxes on these new boundaries I introduced. How to do it? What we do is we make sure that that element there is in equilibrium or locally conservative. That now determines that flux. That one there should be conservative. That determines that flux. This one here as well. Those 3 fluxes are determined. The one in the middle will automatically be conservative because the fluxes for the whole element were. So I introduce 3 fluxes in there. I calculate the same matrix as before. I don't have a different matrix for each of those elements in the submesh. It's the same matrix as for the original one. I define a new vector of fluxes by just taking these 3 values, putting them in a vector. I work that out, and then I sum it over the 4 triangles, and there's a scaling factor of 1/4 to account for the fact the areas change. I do essentially the same thing. I didn't have to construct a virtual mesh. I didn't have to do any kind of computation other than identifying those new piecewise constant fluxes, which, that's just literally 4 lines of code. I take the same mass-like matrix as before, and I calculate that. It's essentially for free. I didn't work too hard there. I didn't generate any meshes or anything.
If your element's bent, do you have to do a different calculation in each format?
Say again?
If your element was bent, so space...
Curvilinear elements. That can be done, and now you'd have to have a different M.
Yeah.
But yes. Yeah. Same thing for more levels of refinement. So you introduce that virtual mesh. I now have got 4 times the situation I described on the previous slide with 1 hanging node. I do what I said on each of them and just recurse up this thing. So hopefully you can see, no matter how many levels of refinement you do, I just proceed recursively. This is very nicely to write. The number of lines of code is almost nothing if you write a recursive procedure. Costs virtually nothing to do. Costs virtually nothing. What do you get? You get a guaranteed upper bound on the error, and it costs you almost nothing to do. So splendid. That is more or less how you prove the upper bound. And the thing that strikes me about that is how simple it goes. I mean, for decades, very clever people were working a posteriori estimates and getting results that were weaker than this, essentially because we were looking at the problem in the wrong way. Of course, this doesn't mean the papers we write on this are 3 pages long. These turn out to be long, and what kills you is proving that this bound is efficient. It's one thing to have an upper bound. Is it a good one? To prove it's a good one is where the trouble begins.
What's the meaning of the word local when you say local lower bound?
Local lower bound. If you calculate this eta on an element, suppose it's large, does that tell you that the error is large on that element? It doesn't, but what it tells you is that the error is large on that element and the neighbouring ones. So it's telling you that this isn't saying that it couldn't be that it's saying the error's large over there when it's not. It's really telling you that the error's got the right distribution. That's essential for proving convergence of adaptive algorithms. So I'm not emphasizing that too much here, but that's a killer to prove. That's always a lot of trouble, but it's absolutely necessary. Okay, what about the non-conforming error? Pick your favorite test function. You can choose 0 if you wish. Choose any conforming function. Go back to this non-conforming error. Satisfies this. This is really remarkably easy. I mean, just look what happens. So what we do is we put this function you like in there and we take it out. I always joke to my students when I'm teaching mathematical analysis that the only trick you need to know is the triangle inequality and adding 0 to things. Here we're adding 0 to something. What about this extra term in red? It's the gradient times the curl. It's 0. So I added that. And now if you look, what's happened here is this is the thing I'm trying to bound. And now I know everything over here. This is my finite element approximation. This is something I get to choose. Crank out Cauchy-Schwarz. We didn't lose anything yet. If you're clever enough with your choice of U star, if you choose it to be U minus chi, that should be. Yeah, U minus phi, the thing that was before, then this is an equality. So there's nothing lost here, provided you make a smart enough choice of this. This is what you're trying to bound. That is the minimum over all possible choices of U star of something that's computable once you've made your choice of U star. So if you make a particular choice of U star, you may hit the minimum. If you don't, you'll be a little bit bigger and you'll get an upper bound. So that's the idea. Take any approximation to U, you obtain a computable upper bound simply by working out that. The devil is how to get a good bound. If you choose U star equal to 0, you'll get an upper bound. It will be an awful bound. How to choose U to get a good bound? You could work hard here, but I don't want to work hard because I've already worked hard to get the finite element approximation in hand. I've got a lot of information about U because I've got my finite element approximation of U. Can I make use of that to make a sensible choice of U star? U star has to be smooth. UP is not, so I can't just choose U star equal to UP. So what I need to do is probably try and choose U star close to P by maybe smoothing it or averaging it. So that's what we do. So UP is known but discontinuous. How to figure out what U star should be. Introduce the virtual refinement. What we do is we define U star to be piecewise linear on this virtual mesh here. We're never going to construct U star, but we will define it. Now we've got all of these nodes around here. What we do is we take the value. So to define a piecewise linear function, I have to tell you its value is at all of these nodes. Value there is taken, what I do there is I just average the values around. So I'm getting a discontinuous approximation. I get a different value from each element. I simply average those things. So I just average there to work out those. And at the hanging nodes, I also just do an averaging. So at these hanging nodes here, I just average around the thing. These are a little bit more tricky. What do I do there? At the interior ones, I just take it equal to UP because there's no competing value. Remember, it's a single affine function there. I just take U star to be equal to UP there. And at these nodes here, I do it by interpolation. The reason I do it by interpolation is I have to bear in mind what I did in the neighbor. There, I'm doing a piecewise linear approximation which interpolates that value and that value. In order for it to match the neighboring one, I should interpolate linearly, and that's what I choose here. So a very simple smoothing operation. And on the Dirichlet boundary, I take it to the data. That gives me our U star. I can compute this thing. It's piecewise linear. That's piecewise linear. The computation of that is very fast. I just use the existing element stiffness matrix if I like. And what I get is a guaranteed upper bound on the conforming error. Local lower bounds again. Works for non-homogeneous Dirichlet data and so on. What do I get for all of this? If I add my estimator for the conforming error, the sigma thing, and then the thing with the smoothing, add them together, that was the sum of the squares of the conforming error and non-conforming error. I have a bound for each of those, add them up, that's a bound for the whole thing. And the question is, does it really control the error? There's my computable upper bound. You calculate that, and that's a guaranteed upper bound. That's the main result. There's some philosophical issues here. Does this really control the error? Because if you look at the broken energy norm of the error, it's not actually a norm. You put in a piecewise constant function, the broken energy norm of a piecewise constant function is 0. Does it make sense to estimate the error in this norm here? Maybe what we should do is to estimate the error in the DG norm. You can do that as well, because the extra term in the DG norm, you just add something. So does it really control the error? Well, one thing is we could estimate the error in the DG norm. Kappa is known, H is known. The jump in the error, well, U doesn't have a jump. So the jump in the error is simply the jump in the finite element approximation. So that we can evaluate exactly. We have a bound for that. We can work out that. We have a bound for the DG error. So we could do that. There's the bound. It's just the jump in those things. It costs virtually nothing to do. But who cares about the DG norm? There are many papers estimating the error in the DG norm. Who cares? If I talk to people who have got to certify whether a pipe's going to fail, they don't care about the DG norm. It's useful for proving a priori convergence, but does it really make sense to have a computable bound for that? You can have it if you want. For me, it doesn't make much sense. Not everyone agrees with that. But, my philosophy is slightly different. I argue that these are already bounded, because what we're doing here, here's another result. Again, for kappa sufficiently large, this was a new result which I proved 8 or 9 years ago. What it shows is these jumps in the error are already bounded by the estimator. So you don't need to add these things in. They're already bounded by that. And what it shows is that it makes sense to estimate the error in this norm here. So that's kind of a philosophical point that I won't go into. Simple problem, does it work? Those are the meshes. Do a fair bit of refinement. Basically, we've got a bump in here and nothing in there to try and generate a lot of hanging nodes. How good are these bounds? What we've got here, we're doing symmetric interior penalty Galerkin. That's the true error. This is the energy. This is the norm of the true. This is the value of the norms. This is the number of degrees of freedom in those various meshes. That's the true error there. What is our estimator for the true error? It's that green line there. So not too bad. It's not equal, but we're only asking for an upper bound. This is due to approximation of the data. We also take that into account. That's higher order, so I won't dwell upon it. This is the true error measured in the DG norm. Our estimator for the error in the DG norm is there as well, so we also have an upper bound for that. How close is it? Starts off, we're overestimating by a factor of 5, but this is a mesh with, 5 or 6 degrees of freedom. Very quickly, we're down to overestimating by a factor of about 1.5. If you can do better, fine, that's all right for me. We're overestimating by about 0.5. I'd like to do better, but that's all right. Here's a problem where we're going to change the order. So we have a singularity here. What I've said today, so far today, is just for piecewise linear approximation. We have all this theory for arbitrary order approximation, arbitrary order non-uniform approximation. That's what I'm going to show you results for here. So the deal here is there's going to be singularities there. There are going to be weaker singularities around here. If you're using piecewise linears, you would never bother to refine around there because those singularities aren't too strong. But when you go up with the order, it makes sense to do H refinement there rather than P refinement. So that's after one loop of the adaptive refinement. You see that what we've done is we've realized that there's a singularity, so we're doing geometric refinement there. There's a lack of smoothness, so we've raised the order of the method locally. We then go again. It's now raised the order locally in more elements. It's raised the order again there, and it's done more geometric refinements there. And it's also beginning to see this singularity here. And as we go through this, we get these meshes. So now it's raised the order to 4 around there. Those elements don't touch the singularity. There's another P equal to 4 element there. Some geometric refinements around these. It's beginning to see these singularities. Off it goes. And we're up to 6. And we've run this up to whatever order you like. What's the reason to do HP refinement? This is the number of degrees of freedom. This is the error. Log scale. This should be a straight line for algebraic error. It's not. It's exponential convergence. This is why you do HP refinement, because you can prove if you do it in the right way, you'll get exponential convergence. This is the true error here. You see it's converging exponentially fast. This is our estimated error That's converging exponentially fast, and it's an upper bound again. It overestimates by a factor of, well, for the, one's for the DG norm, one's for the broken energy norm. This is the broken energy norm. It's overestimating by a factor between 1.45 and 1.7. Not bad, considering the nature of the approximation. All right, so that's a simple problem where relatively simple scheme. I've shown you what we can do. I've given you a flavor of the proof. Hopefully you know what I'm trying to, I hesitate to use the word sell, but that's basically what we've got for all kinds of different schemes, different problems. I don't care about the Poisson problem. We did the basic analysis there because the problem was to try and figure out what the property of the scheme is that you need to use and how to efficiently exploit it. So we did that for conforming methods, non-conforming, mixed, DG, essentially every kind of scheme we could dream up. Then the issue was to try and see what happens when we look at more complicated problems. For example, things like elasticity, where we've now got a system, a more complicated operator, more complicated constitutive equations. We were able to do that. I could show you results on elasticity. I decided not to. We get guaranteed upper bounds for that. We've also looked at problems where we have reaction-dominated type problems, where you have a very large absolute term. The question there is, does the upper bound degenerate as the reaction term gets larger and larger, and we have fully computable, robust bounds which are independent of the size of the reaction term? I wrote a paper with Ivo Babushka in '99, which was essentially the first one to get a computable upper bound for the error in those things, which was robust. Actually, the bound there wasn't really computable. We owned up to this in the paper and said, we'll sort this out in a later paper. That later paper came last year. Slight delay of 14 years, but we now have computable upper bounds which are completely robust for reaction diffusion problems. This is now some work I've done with a student of mine back in Chile, my ex-colleague at Strathclyde and Rankin again, where we looked at convection diffusion problems when we're really thinking about the convection-dominated case. So there's going to be diffusion in there, but it's not going to be diffusion-dominated. We did that in a different situation. We're going to use a stabilized scheme. You can't just put in your... Well, we're going to use a stabilized finite element scheme. So here we are. It's a scalar problem again, but the key thing now is what happens as this parameter gets very large or this one gets very small. So usual types of business. We're going to stabilize this thing with a stabilizing term of this type, the usual type of stabilization. Don't want to bother you with the details of that. So there's a residual is in there. There's something which measures this. So it's essentially like a least squares type stabilization. There's so many stabilization schemes I can never think which is which. Let me go through all the same kinds of things. The main objective is to get a guaranteed bound. It should be fully computable. Again, what we compute should be an upper bound for the error and it shouldn't cost much. It should be locally efficient. The estimator on element k should be a lower bound for the error, not necessarily on the element, that would be too much to match, but the error on a patch of elements around k. That's what that would say. There, I don't know what the constant is. But I don't need to know what the constant is because when I'm doing my adaptive refinement algorithm, that will come into the rate of convergence of the adaptive refinement, but I don't need to know what it is to apply it in practice. I don't need it as a stopping criteria. That's what I need for a stopping criteria. So it should be locally efficient. And then, well, aposture estimation for convection-dominated problem has been a bugbear for many years. To try and get something that's robust, it's caused a lot of heartache. And, well, I guess the breakthrough, to some extent, was made by Rudiger Verfurth, and he showed that really the way to estimate or what you're trying to get is a robust estimator. So you want something that estimates the true error with constants that don't degenerate as the material properties get worse, or the convection gets bigger, or the diffusion gets smaller. So that's what this is saying. So what you've got is the usual energy type norm. Let me just go back and show the energy type norm there. So it's just nu times the H1 part plus the absolute term times the L2 part. So you have that one in, and then you have this additional term. And this, in some sense, is a mathematical invention I mean, the question, I guess, for answered is, this is what I'm computing, what does it estimate robustly? And it estimates this robustly. So this is the dual norm of the streamlined derivative of the error. So that, I don't particularly, that's just the best that's known. So we don't want to do worse than what anyone else has already got, so we should be estimating two sides with respect to this funny looking norm here. But the norm that I'm going to really estimate, again, if I talk to people in industry, they're going to say, well, what the heck's that? What's that got to do with my life? This thing makes more sense to them, this energy type norm. So we will get a guaranteed bound for the error in this thing, but we'd like it to be robust in some sense, and that's the sense in which it will be robust. So here we're using a stabilized approximation. It's a conforming approximation this time. And the problem now is that we're still going to have this local conservative property. Now, continuous Galerkin is not locally conservative. It's just not. But we need a locally conservative flux. And this can be manufactured. And there's a way to manufacture that thing. What you do is you do some local post-processing of your finite element approximation to create some fluxes. These fluxes are consistent in that the flux from element K to its neighbor is minus the flux from the neighbor into the element, so it's consistent. It agrees with the true flux on the boundary, and it satisfies this local conservation property. That is not available to you for a conforming method in the same way as it was staring in the face for DG. You have to manufacture that yourself, and we've developed algorithms which are optimal for that. And so that can be done. And then it basically goes the same as before. And what we have is this thing with the sigma. The sigma is a bit of a mess to calculate now, but again, its norm can be computed efficiently without obtaining sigma itself. So this can all be computed again. How good is this bound? Well, it's an upper bound, and it's a local lower bound in this sense. And what you see here is there's the Peclet number appearing. So if the Peclet number is large, this lower bound is not going to be too good. What it's saying is that if you estimate there in the energy-like norm, you're going to get a local overestimation proportional to the Peclet number. But that's if you want to measure in this energy-type norm. If you measure in the crazy norm I showed you a minute ago, then it would be robust. So anyway, there's a long proof of that. We've tested it in cases where we know the true solution, and it does give upper bounds which are robust. Here's a problem which I asked a student to solve. It's kind of a bit of a silly problem in some ways, but what we have here is a building. I said, make it look like the Empire State Building. That doesn't look like the Empire State Building, but anyway, it's a yes, B problem. What we've got here is we're going to put temperature equal to 1 on there. We've got the wind blowing, I guess it's from the north if it's the Empire State Building, so the wind's blowing in there, and then we've got it in a box. We're just going to put various boundary conditions to make sense. We're solving this with really in this absurd limit where we've got diffusion down to 10 to the minus 12 and the wind is 100. This is what you get for the isotherms. So you can see this really is convection dominated. So you get this just propagation of heat downwind, temperatures 1 just downwind, and then very steep boundary layers between the two. This is a mesh over the Empire State Building, would you believe? So that's, because it's a 3D problem, it's always hard, I never know how to show the meshes, but that's what the mesh is on the building. If we do a zoom to that top part, you can see that we're getting a fair amount of refinement on that. This is looking downwind. So this is standing north of the building, looking down just a little bit, and you can see there's already been a very small amount of diffusion. The mesh, a section through the mesh, as you see, it really tracks the outline of the building. Just a little bit down. We go a bit further down, a bit more diffusion. The mesh becomes a little bit more diffuse because what's going on. A little bit further down, same kind of thing. So this is, well, in many ways it's a toy problem, but it is in 3D. What we're getting is fully computable. It works for the stabilized method. We've done a problem in this absurd limit here. I mean, this is very difficult to get anything of any sense for this. The danger is that if you start with a very coarse mesh that doesn't really resolve the solution like we did here, that because your error estimator may not be registering what the true error distribution is, it could kind of get fixated and find some artifacts which it then refines due to the basic instability of the problem. It then generates more spurious features, the estimator picks them up and it refines further and further and just does refinements in the wrong place. We didn't start with a reasonable measure. I didn't show the original one, but it was very, very coarse. And we're solving a problem where it's really very convection dominated, and yet we're still getting something reasonable using this estimator as a guide. What we're getting is a guarantee bound on the error. We don't know the true error for this problem. We've done overkill solutions, but we don't really trust them because it's such a difficult problem to resolve fully. We've solved problems where we do know the analytic solution and we are getting guaranteed upper bounds. They're about 1.4, 1.5 again over estimation. So this is just a snapshot of where we're pushing things. We've done it for all kinds of different problems. I'm interested to see whether there are new schemes where we can try and look into the scheme and see what the key property is and pull it out and try and get guaranteed bounds. That's a problem I'd be interested in looking at. New types of problems where you're using, for example, DG or whatever. Can we get guaranteed bounds for the problem you're interested in? All of these are things I would be interested in talking about while I'm here. I'm also interested in talking about spectral element methods for wave propagation problems, for all these kinds of things. So I've never finished early before. Never finished early before. So I thought I was going to be out of time here. So I had another slide where I guess I don't want to oversell. So what I've shown you here is a problem where all of the constants can be obtained. So the constants, you have constants coming from the nature of the problem. If the problem has some, at the continuous level, has some underlying instability, then that's going to be reflected in the nature of the problem. When we do Stokes, for example, the im sup constant for the continuous problem comes into it. There's no way to avoid that. That's telling you something about the nature of the underlying problem. That can't be taken away when you're looking at bounding errors and so on. So that has to come in. So I guess my quote would be something like, some of the constants can be found all of the time. All of the constants can be found some of the time, even if you can't find all of the constants all of the time. So with that, I should cut my losses and just stop right there. So thanks very much.
Questions from Mark? Colin?
Your L-shaped example, you were doing H and P refinement.
Yes.
Yep. Are you using your estimates to guide whether you should be doing H or P refinement?
Yes and no. For that problem, there's some work I did with a student of mine 10 years ago, Bill Senior, where the question then was, if you're doing an upholstery estimator, you now have a decision. So this tells you the error's bad in an element. Should I do H refinement or P refinement? This is basically the question you're asking, right?
Yeah.
So what we did there is we used the estimator. We basically examined the sensitivity of the estimator to raising the order and lowering the order locally, and we had a procedure for doing that. And based on the way that was behaving, we were able to make a decision on H versus P. And that works very nicely for convection problems, all of these things. Now, what we also did at that time is what I call a tagging strategy. Because for these types of problems, the elasticity problem I showed you here, you know where all the trouble is. It's at the re-entrant corners. There's no features generated by the nature of the problem, no internal features. So I know that if an element is targeted for refinement, if it's at a re-entrant corner, then there's a singularity of some strength or other there. And there, the a priori convergence theory tells you should do H refinement. Whereas everywhere else, you should do P refinement. So in that case, we didn't do this basically trying to identify H versus P using the estimator. What we did is we tagged all of the vertices that could be trouble spots. So all of those corner ones. And then each element had a flag, and it said, if you've got one of these bad corners, then you do H refinement on it. And the reason we did that is that we found that we could generate the same kind of meshes using this very sophisticated algorithm, but just doing this basic naive tagging strategy, we could do at least as good.
For that problem, you know beforehand from
Exactly.
competition what the problems are
Exactly,
going to be.
yes.
Okay.
Yeah, for that type of problem. But for maybe if this was non-linear or something where there might be some interior feature that's been generated and that you might not know it, and in that case, there's a more involved strategy that we have that tells you whether to do H versus P. And that comes from the estimate, and basically by looking at the sensitivity of the estimator to raising P or lowering P. And we can do that adaptively as well. So, as I said, I'm a lazy guy, so for this problem I didn't want to do that, so I just did the simple tagging strategy. But it's amazing how far that tagging strategy goes. There are a lot of problems where you more or less know a priori what to do. The question is how much to do. So if you've got one L-shaped domain with a corner, you know you're always going to do H around there. I don't really need a lot of information. There's a lot of problems where you have a priori information you should use, and I'm not above using that. Very big class is a problem. If I don't, then I crank out the full thing.
I think for these kind of aerodynamical problems, you know that the problem's going to be near to kind of the cusps on the back of the aerofoil.
Yes, so that would be a definite case for a tagged vertex. But if my policy is if you've got a priori information or a priori knowledge, build it in. Don't need to compute it again.
Okay.
How difficult would it be to include this, the estimate for the convection dominant case into what Siebert and Kreuzer and co-workers have done for the heat equation? I mean,
So
get an estimate for time dependence.
So that's a good point. In fact, I'm glad you raised that because I haven't mentioned any type of time discretization here.
Mark, question?
He was asking whether this could be incorporated into, if we basically had a time derivative in this and made it into like a parabolic problem. So I don't know exactly what they did, but our policy is that we break the error. You've got different types of discretization here. You've got temporal errors, you've got spatial errors. We're estimating the spatial error here. There is an issue of balancing the two. And the same thing, if you're doing modeling, you've got a high-dimensional model which you then approximate with a model of parameter of models, and then you've got discretization, and you can kind of balance the two. Time discretization is another source of discretization error. We don't, I mean, the way that, the kind of the taxonomy that people use for extending this to time discretization errors, they take it as a sequence of time stepping, and then they're basically left with estimating the error in what can be thought of as being a steady state problem at each time. So basically the time derivative goes across and it's treated as a modified residual. That would work exactly the same. So basically you're thinking about these reconstruction procedures of Niceto and Makridakis and so on. It just go the same. You know, they used a different way to estimate the spatial type of error, but you could just plug this in, and I don't like to say it can definitely be done, but I would be very surprised if it didn't. So I think it would just fit in. And that's really why I don't concentrate too much on time errors, because there is more or less a well-established framework that allows you, if you've got a good spatial estimator, to get a good time, to couple it with the time as well. So thanks very much for that. I'll give you the money later.
I don't know if this is true or not, but I have the impression that the state of these kind of estimates and convergence proofs for the finite element and discontinuous Galerkin is much, there's a lot more proofs as compared to the finite volumes on unstructured grids.
Yeah.
Is there a reason, a mathematical reason for that, or a?
Not really. I mean, in many ways you can think of DG as some kind of finite volume thing anyway. All of this can be pushed through for finite volume. The reason I have finite element is that that's the way I was brought up. I mean, there's nothing stopping this from going through to finite volumes. I mean, that's really not a sensible statement, because there's so many different flavors of finite volumes that it's almost certainly not a correct statement. But for certain types of finite volume methods, this will just go through on the not. There may be certain variants that you have to do a little bit of thinking. There's some work by the French school, Alexander Ern and Martin Borolik. They basically push this methodology through for certain types of finite volume schemes, and there's really no particular technical difficulty. Again, the details are devil's in the detail. What is the key property you want to exploit from the finite volume? Local conservative again. That's why I said similar to DG. But there's no real, there's no big problem. There are lots of minor issues, but there's no real big issue to break that. Is that what you're asking?
Yeah.
Yeah. Okay.
Yeah.
I want to ask again about the time, or about generalizing it to the time-dependent problem.
Yeah.
And there is now big effort in weather forecasting done by making many forecasts, many numerical forecasts, in order from the spread to make conclusions on the error. And if now you simplify the problems by leaving away the so-called physics process like radiation, which really make a mess of it, if you think it's just a Navier-Stokes fluid which is going on, do you think you could replace these many calculations which are done to estimate the error by just an estimate, and the estimate would even be more accurate than...
So you're thinking about the situation where you might have uncertainties in the data and you're basically trying to get a sensitivity?
Yes.
I mean, that's a very good question as well. I mean, this is, roughly speaking, I would say that the types of things I've talked about today are more or less regarded as not being the bottleneck anymore. The kind of issues people are talking about now are these validation and verification type things where you have uncertainty in the data and you may actually cast your problem as a probabilistic or stochastic setting. And then the question now is to estimate yet another source of error, the uncertainty. I think that's a different kind of animal. I mean, these would play a part in it, in that if one way to take account of uncertainty in the data is to cast the problem in higher dimensions, and then you may use these techniques to estimate the spatial, the discretization error of your high dimensional problem. But these aren't really saying anything about the uncertainty in the data. Well, in a rigorous way, it may be possible to do something heuristically, and I think, you know, and I wouldn't, now you've got me, the more I think about it, there may be something to be done there, but I don't know how to do it, I haven't thought about it. But there are people who are worrying about uncertainty in the data, but they're dealing with it in a different type of way. They regard it as a different type of animal, it's a probabilistic type of thing. But these would play a role in estimating or quantifying the discretization error. The uncertainty error is something that would be treated in a different way. So I didn't really answer your question because I should just say I don't know.
Great. Well, thank you very much. You're no longer under time, so I'm going to kick you off.